Okay, so now we've got the community model. Now we've got Mizer running and we've done one example with the community model. Let's have a look at something a little bit more involved. So what we're going to do is change the way we're fishing on this system and have a look at the consequences. And we're hoping to see a trophic cascade. So we'll make a new params object. We can call it anything we want, but let's call it params knife. And that's going to be defined as the output of this set community model. And we'll have some various parameters. Z0 is 0.1. Recruitment again for times 10 to the 7. Again, alpha is 0.2. F0 is 0.7. But now we're going to set the knife edge size to be equal to 1000. And what that means is that our fishing gear is going to start affecting fish when they get over 1000 grams. So we'll define that object. And now let's use it for a simulation. We'll call it simulation sim0, and it's defined as the output of running project that evolves our partial differential equations and simulates the system. And the params object is this params knife, and we're going to have no efforts again initially. And we'll run it for 50 years. Okay, now let's make another object. I just pressed up on the keyboard, which gives the last command back from the console. It's quite useful to save time. So it's a similar command, but now we're actually going to put a fishing effort of 1 into this. So in the previous simulation 0, there wasn't any fishing. In this one, there is. Okay, so let's have a look at this simulation 1, which includes fishing. Now recall from the last simulation, this is the second to last one, but similarly there wasn't any fishing mortality because the fishing efforts were 0 in that case. But now we'll plot this one. And you see this state is a little bit different, and now there is actually some fishing mortality, which is kicking in beyond 1000 grams. So we have these two simulation objects here, sim0 and sim1. Let's have a look at sim0. And one of the slots of that is called N. This keeps track of the abundance of the different fish over time and different weights. It's one of the most basic and important objects in Mizer, although you might not have to interface with it too much. It depends what type of commands you want to do. But it's a very important thing because it essentially records how the abundances of fish change over time. So we have this object. If I just press enter, you'll see a great mess of different numbers and different dimensions. It won't be too hard to understand. Better to do this dim command upon it. That shows us the dimensions of this object. And we see it's 51 by 1 by 100. So this first number here is the number of time steps involved. The second number is the number of species, and the third number is how many weights classes there are. Those are corresponding to these entries of params at W, these different sort of weight bins that we're interested in recording the abundance at. So, well, I guess I'll just show you this. So this is, if we go sim 0 at n, open square bracket. So we want to look at, let's say, the final time step and the first species, and we'll just put a gap here after this comma to show that we want to select all of the entries in this third dimension, and we'll press enter. Well, we get a list of the abundances of this thing at all the different weights on the final time step. So we can combine this with the other command. So if we use this plot function, for the x coordinates we'll use params at w, and for the y coordinates we'll use sim 0. We'll use this same thing we just did. So this is basic R programming to make plots. If you want to make a kind of point plot, then you have a list of the x coordinates and a similarly length list of the y coordinates. That's the basic way to do it. So if we press enter, that gives us a plot of the abundances at different weights. Now it's not very easy to see at all, and that's because of the huge orders of magnitude that these quantities are varying over. So it's better if we do log. We do log plots. So we'll log the x and the y, and there you see a bit more sensible plot showing the abundance at different weights. You don't really need to know how to do those basic commands, but it's useful if you do. Okay, so now let's do something a bit more interesting. We did that simulation sim 0 with no fishing, and we've done another simulation sim 1 with fishing. So let's plot the relative abundances between those simulations. So we'll type relative, we'll make a new thing called relative abundance. And we'll define that as sim1 at n on the final time step, the 51st time step. Divided by the abundance without fishing. So that would be the same thing but with sim 0 instead of sim 1. Okay. So now let's make a plot of this, well, our x coordinates. Okay, I should have done x equals. Let me just say this. So I did this command a moment ago, and I could just as easily have said x equals this and y equals this. Okay, it's the same command. Right, so I want to do a similar thing now to plot the relative abundance. So x is equal to this params object is also stored in various ways. So these weight W bins, we can also access them like this. So we can say at params and then at W. So basically this params object I was discussing associated with the simulation is actually stored as a slot on this simulation object. And then within that there's another slot which is the weights. So it's just a fancier way of saying this basically. Anyway, so they're going to be our x coordinates. Our y coordinates are going to be these relative abundances, and let's just log the x coordinates here, the weights. set the type of the plot. Oops, I pressed return prematurely. We'll add some plot labels. So this is going to be the size in grams. And the Y label, we'll call it relative abundance. So that makes our plot, but because we did type equals n, it's not actually showing anything at the moment. So what we'll do now is add some lines to this plot. Like so. That shows us the lines for our simulation. And let's add some more lines. Well, no, that'll do